In this video, we're going to take a look at how to use definite integrals to compute the arc length of a curve in the plane. We can think of the arc length of a curve as the distance that you would travel if you were walking along the path of the curve in the plane. Or, thought of a different way, if we wanted to lay a string or rope or wire or something like that along the curve from one point to another, the arc length of that curve would be the length of string or rope or wire required to do that. In order to find the arc length of a general curve in the plane, we're going to start by considering one of the simplest curves to find the length of, that is, a line segment. Here we see a line segment in the plane with one endpoint at x1, y1, and the other endpoint at x2, y2. And you might remember there is a distance formula that will allow us to compute the distance between 2 points in the plane. And if we have a line segment like this, that distance formula will give us the length of that particular segment. So applying the distance formula here, we see that the length of this line segment, which I'll call lowercase l, is going to be the square root of the difference in the x values squared, so x2 minus x1 squared, plus the difference in the y values squared, y2 minus y1 squared. And this expression here is just the standard distance formula for points in the plane. Now, we can simplify this a little bit by setting dx to be equal to the difference in the x values, x2 minus x1, and by setting dy to be the difference in the y values, y2 minus y1. And by substituting these in, we see that the length of this particular segment is going to be dx squared plus dy squared, all inside the square root function. So this length here will give us the length of the blue line segment at the top of the screen. Now that we have a nice formula for the length of a line segment, we're going to use this to first approximate and then find the exact value of the arc length for a general curve in the plane. Here we have the graph of a function f of x drawn between x equal a and x equal b in the plane. We would like to find the arc length of this particular curve. So in other words, if we started at the point corresponding to x equal a on this graph and walked along the graph to the point that corresponds to x equal b, we'd like to determine the length or the distance that we traveled. We're going to approach this in a similar manner to how we approached the problem of finding a volume of a solid. We're going to break up the interval from a to b into n subintervals of an equal width, and we're going to call that width dx, just to give that common width a name. So in our picture, we're going to break up this interval into 4 subintervals at the red tick marks, and we'll note that the distance between each of these tick marks is by definition dx, since these are equally spaced out. Once we have our interval a to b broken up into subintervals of our equal width, we're going to look at the points on our curve that correspond to the endpoints of these subintervals. So these would be the points that are being shaded in red. So at the end of each of our subintervals, we find the point on the curve and mark that point. We now form line segments between consecutive pairs of these points. So from the point at A to the point at the end of the first subinterval, we form a line segment there. And then from that point to the endpoint of the second subinterval, we form a line segment there. And then a line segment from there to the next point, and from there to the point corresponding to B. And so here, with our 4 subintervals, we have formed 4 line segments between points on our curve, and the length of each of these line segments is approximately the length of the curve along the same subinterval. Now, obviously, those are not exact values. The line segment and the curve are going to be slightly different, but it is a decent approximation for the length of that curve. And the nice thing about using line segments is, as we've already seen, we can easily compute the length of that line segment. And so the idea here is that we're going to approximate the length of our curve by the sum of the lengths of these line segments, and then by making more and more subintervals, the line segments will be closer and closer to the actual length of the curve. And so applying a limit, we can get the exact value. So for notational purposes, let's let L sub k equal the length of the kth line segment in our approximation. So in our picture, L1 would be the length of our first line segment, L2 the length of our second, L3 the length of our third, and L4 the length of the fourth segment. And so here the length of our curve is approximately equal to L1 plus L2 plus L3 plus L4. Although we used 4 subintervals in this particular picture, we're going to do the computation based on an arbitrary number n of subintervals, and then ultimately take the limit as n goes to infinity to find the exact value. By approximating our curve with line segments, as we've just demonstrated, the length of the curve L is going to be approximately equal to the sum of all of the lengths of our segments. Since we have n segments that are approximating our curve, and L sub k is the length of the kth segment, our arc length L will be approximately equal to the sum from k equal 1 to n of L sub k. Now, earlier we saw the length of a line segment was given by the expression square root of dx squared plus dy squared. Now here we're going to denote dy squared actually by dy sub k squared. And the reason is that for each of our line segments, the change in y is going to be different. However, notice that I did not put a subscript of k on the dx here. And that's because when we formed our subintervals, we chose them to all have the same width, which was dx. And so regardless of which line segment we are considering, the horizontal change between the endpoints of the line segment, in other words, x2 minus x1 for each segment, is going to be a constant value dx for every single line segment, whereas the vertical distance between the endpoints will often change. And so here we can leave the dx without a subscript, but the dy does need one since it will be different for each of our segments. So at this point in the computation, we need to use a result from Calculus 1 that you've certainly seen but have probably forgotten about, specifically the mean value theorem. So in the context that we're working, if we're on if we're on a particular subinterval from x sub k minus 1 to x sub k, so this is just one of the subintervals that we formed in the earlier step, the mean value theorem is going to guarantee that there exists some number that we'll call c sub k in that interval with the property shown here, that the derivative of our function f at that point is equal to the slope of the line segment between the endpoints. And so that slope there would be f of xk minus f of xk minus 1. That would be the difference in the y values, or dyk, the difference in y's on the kth line segment, divided by xk minus 1. And that would be the difference along the x-axis between the x values of our segment, which we were calling dx. And so what we have here is that there's some point ck, this number, where f prime at this point is equal to dyk divided by dx, or by multiplying both sides of the left and right-hand side here by dx, we see that d sub y sub k is going to equal to f prime of c sub k times dx. And so here we're able to rewrite dyk as a function value, f prime of some point, multiplied by dx. And now we can substitute this back into our expression here for dy sub k, and we're going to end up with just dx again instead of a dy sub k. So making this substitution, we see we have dx squared plus f prime of ck times dx, quantity squared, all there inside of the square root. Now, looking at the square root itself, inside there, we see that each term is going to have a factor of dx squared. And so we can actually factor out a dx squared. From the first term, that's just going to leave a factor of 1. And from the second term, we're going to just have f prime of ck, quantity squared. And so we have this expression here. And now we can bring the dx squared outside of the square root by evaluating the square root of a perfect square. And we're going to end up with 1 plus f prime of c sub k squared inside the square root, and a dx outside of our square root like this. Now this expression here at the bottom is an example of a Riemann sum. And so we know that by taking the limit as n goes to infinity of this sum, we're going to get a definite integral from a to b, which was the interval on which this sum was based. And by doing so, we're also going to make the approximation of our arc length into an exact value. So by taking the limit as n goes to infinity in that Riemann sum, we can see that the arc length of a function y equal f of x along the interval a to b will be given by the definite integral from a to b of the square root of 1 plus f prime of x squared. So that's 1 plus the derivative of our function squared. Alternatively, if we want to use a different notation for the derivative instead of f prime, we could represent the derivative as dy dx, and in that case, we get the integral from a to b of the square root of 1 plus dy dx squared dx. Note that these two integrals are exactly the same. They just use a different notation for the derivative of our function y equals f of x.